NanoHub U, online instruction.
Hey everyone, welcome to the course. This is Nanophotonic Modeling. I'm Peter Bermel, the instructor, and I teach at Purdue University. What we're going to be talking about in our first unit, Unit 1, are band structures. And then, of course, in the subsequent units, we'll go over different topics. And so after band structures, then we'll go over transfer matrix methods. And then in the third unit, we'll talk about finite difference time domain methods. And then in the final unit, Unit 4, we'll actually talk about some advanced multiphysics problems and finite element methods to solve them. So now let's get started with the band structure problem. So what is the band structure problem? So it's basically an eigenvalue equation. And the eigenvalue equation may have this form, h psi equals e psi. So we interpret h is a matrix or an operator, and then e is a scalar or a number, essentially. And so what's interesting about the eigenvalue equation in general is that you end up, when you multiply h times psi, you still recover that psi times a constant. And so, of course, there are many different types of band structure problems that we could potentially consider. One famous one, of course, is Schrodinger's equation. And so Schrodinger's equation looks like this. It has both kinetic and potential energy terms equal to the energy of the photon or electron of the system. And then you have a photonic band structure, which is basically given by combining Maxwell's equations. So this is almost like, but slightly different than the Helmholtz equation. And then you have the so-called phononic band structure, which describes quanta of heat that would propagate in any kind of solid material, for example. So now we're going to talk first about Schrodinger's equation, which will kind of help us understand the basic premise of the band structure problem before we go into photonic band structures. So basically, Schrodinger's equation describes the wave function psi to tell you the extent of the particle. The probability of finding a particle at any given location, it goes like psi squared. So of course it has to be normalized. So integrating over all space would give you a probability of 1. So it has to be somewhere. So then when you write down Schrodinger's equation, h psi equals e psi, like I mentioned, it has kinetic and potential terms. So of course, you know, in classical mechanics, that kinetic energy goes like 1/2 mv squared, or also can be written as momentum p squared divided by 2m, right? So that's this. However, in quantum mechanics, usually you promote what would normally be just a simple number like momentum to an operator. And so when you call that operator minus I h bar times the gradient function, or nabla, then you get something like the p squared becomes like minus h bar squared times the Laplacian, and then you divide by 2m to get the kinetic energy. And so if you didn't have any potential, then that would be your full Hamiltonian. And so then the Hamiltonian would look like this kinetic energy operator times psi equal e psi. And so then if you think about it for a minute, you can imagine, based on analogy with, say, electrostatics, that your solution would just be a plane wave. And so if you actually substitute this expression that psi goes like e to the plus or minus ikx, then you can see that this Laplacian brings down a factor of minus k squared. And so then you get h bar squared k squared over 2m, right? And so it kind of makes sense because we're applying operators that like the wave functions themselves should be like given by complex exponentials because we recovered the original value. So it's very suitable for these sort of eigenproblems. And the other thing that you notice, of course, is that because E goes like h bar squared k squared over 2m, you have kind of this quadratic curve. And so that's, of course, for particles. If you put the particle in a well, which was infinite, like say a proton in an iron nucleus, then you could basically say that within the radius of the iron nucleus that there's no potential. It basically is stable, but then outside potential is infinite. Of course, this is a little bit of a simplification, but just to give you an idea of what's going on. So there's boundary condition on both sides where psi goes to 0. And so, of course, we can use actually the same kind of solutions that we had before for the free particle, except that we have to impose this boundary condition, which means that eigenfunctions are actually a sum of two plane waves that will cancel out. But then that means that the k values are actually quantized now. And so in order to have basically the psi vanish on both sides, that means we have to have a half integer number of waves. And so then that tells us that k would be integer n times pi over a if it has the length of a. And so then if you plug in the value that we expressed before for the energy as a function of k, h bar squared k squared over 2m, substitute this k value, then you get E is h bar squared n squared pi squared over 2ma squared. So then, of course, we could also do a finite quantum well, like an alpha particle in uranium nucleus. And so here we would say it's very tall, but not infinite potential. And so the difference is just that now it can actually decay exponentially to the outside and maybe even tunnel out, which of course would be classically forbidden if U is greater than kinetic energy, but it's allowed in quantum mechanics. But it may be very improbable, so that's why uranium-235 nucleus lifetime would be on the order of hundreds of millions of years. So a way to actually kind of extend that to a more interesting problem for band structures is to make that whole system that I showed you earlier periodic. So imagine if you had a whole series of periodically repeating wells. And so you have like these little regions where the potential is 0 and it can move freely, but then you have these barriers as well. So then the question is, what would be the boundary conditions that are appropriate for this system? And would each electron get stuck in its own little well? So in the next lecture, we'll actually try to explore how to solve this problem.